OK， 好，同学们，我很难得看到一个科学营队 ，as time goes on， 开始的时间越来越早，因为老师呢，充分具有教育良心。Matt 会有一个5分钟的电影，介绍天文台的，先放给各位看，所以他又不希望这5分钟电影占用他太多时间，所以他会早一点开始放。但是我想，在这个地方。我们就先跟大家介绍一下我的老师 Professor Matthew Malkan， 因为我在1982年去 UCLA 念书的时候，when I began to choose the area， 当我想念我的 research area 的时候，我就发觉我没有别的选择，我就选太阳物理，做太阳。为什么做太阳？我姓孙，孙的英文就是 sun。Yeah, S-U-N. So I have no other choice. I have to do solar physics.But my interest in sun is totally turned off. 所以呢，后来 Matt came to the UCLA. He was that year presidential young investigator. Yeah, 那个不知道每年50万美金，然后有5年的时间，非常杰出的研究者。然后他做的挺好，所以后来我就 join his group and work on quasars with Matt. 好，那我们用热烈的掌声欢迎 Matt。Very much, Weishi.
People seem to like movies, so how about a short movie? It's called Titanic. I'm just kidding. That Alan Stern already did that one, and I'm kind of jealous for Alan Stern because the guy has so many adventures. You know, he's Indiana Jones. So, but I want to just show you that even astronomers can have some adventures also.In my opinion, every night that we go up to a distant mountain for the telescope, which Vishen and I have done many, many times, that's an adventure. But it's a little bit more fun if you make a music video out of it, and that's what this is here. It's a little bit complicated, but speaking of complicated, I have a number of things that might not work on audio-visual. But of course, we already found you can take a risk. Even James Webb Space Telescope takes many risks. I have almost as many failure modes here as they do. We'll see if it works as well. And so I have to explain to you, it's a time exposure movie taken. You will see most of the telescopes working at Mauna Kea almost entirely at nighttime. But of course, to get a good picture, these are long exposure to time exposures. So the lighting, you might be confused. Sometimes it looks like a daytime.That's just because of the long exposure. And you will see alternating period between what look like daytime and nighttime. Don't be confused. What you think the sun is going up or the sun is going down. No, that is the moon going up and going down. And of course, then there are shadows, and it looks like a daytime if you have a long exposure camera like this. So many of the telescopes you'll see here, we have actually heard discussed, and these are crucial, of course, for following up observations that could be made in space. So let's see. First, the night begins as it gets dark, and then the night ends after an amazing night of observing with a lot of rock music. Obviously, it's not that big unless you use a telescope lens.See some of the telescopes on Mauna Kea from a long distance away. That's a view from the shore, ocean. You can still see Mauna Kea pretty well up there. Two Keck telescopes, Subaru telescope, NASA infrared telescope.Had to stick in a volcano. Subaru telescope, nighttime, laser. 2 lasers. What are they looking at? Sagittarius, the center of our galaxy.Continually moving to show you how much time is passing. Galactic telescope, Gemini North. Clouds, we don't like that. There's nothing growing. It's like the surface of the moon. Very long baseline antenna for radio astronomy. The highway, which goes across the island, the big island. Well, it's time to open up. James Clerk Maxwell telescope, millimeter telescope. These lasers are really bright when you stand next to them. Canada, France, Hawaii telescope. Gemini North, again, UK infrared telescope. As you know, Taiwanese astronomers use some of these telescopes, several of them. Venus. The moon. When you stand next to this laser, it's like a sword, a flaming sword, 90 miles long. Night's over. It's time to go to bed. Come down the mountain. He's good, huh? Okay, I had nothing to do with that. Isn't that good, though? I love that movie. Thank you. So I guess you can have a little bit of an adventure just going to the telescope. All right, but this is the biggest venture we've ever done, as you know, in astronomy, and I get to tell you about it. This is my fun. I appreciate it so much. I've been learning so much at this school. It's just such a fantastic time that I've had, so I appreciate being here with you. All right, so you might not realize that the situation for James Webb Space Telescope in some way might be similar to Hubble Space Telescope. Maybe that's before you were born. We remember it very well. But in some way it's different because Hubble Space Telescope was not really working for years. When it launched, it took several years and a number of repair missions to gradually bring Hubble Space Telescope to its capabilities. James Webb Space Telescope, as you will see, starts immediately with all capabilities. So all of the revolutionary discoveries that Hubble made over, I would say, the first 10 years, I expect the same revolution to happen with JWST maybe in the first 1 or 2 years. It's all telescoped together. Well, that's an English pun. So, we can just imagine this. I had to show this picture. You like a few personal pictures here. And because I believe that I am the last principal investigator on the first year of James Webb Space Telescope observations to actually say goodbye to the telescope in person. Yes, of course, I saw this many times during the construction of it in different pieces, in different places, but finally the goodbye was in Redondo Beach here, and I just remember, of course, looking at it really assembled like that and thinking, oh gosh, I can almost not believe this is going to work. That was my opinion. Anyway, just to remind you of some of the many ways that a lot of people were afraid it would not work. Such a gamble. Just the folding up process of this. It's just incredible, the origami that was needed to get a telescope. That's the size of a tennis court. The sunscreen there, which is absolutely essential, has to be somehow folded up into this top of it. This is the biggest European rocket that you can launch. And you see, there's no room for anything there. Okay, this is not like New Horizons. That thing, you could have a party in there. I mean, it's a miracle. It's all folded up. Uh-oh, that means it all has to unfold in space. Nobody can go there to help. It's out of reach. So that is one of the biggest challenges, obstacles that NASA ever attempted. As I understand it, I've talked to a lot of the people, a single point failure is one latch, one motor, one switch, which if it goes wrong, entire project is useless. Entire telescope cannot work. It cannot even be a telescope. There are more than 300 of those single point failures. It's insane. Of course, everybody said to me, don't worry, Matt, each one of these single points has already been successful on some other telescope. But we really cannot usually tell you which other telescope did it, because a lot of those are classified. But nobody ever did 300 together. It's just asking for, you're tempting fate. You are asking for trouble. But NASA was very brave on this, so impressed. So first of all, the launch was absolutely perfect from equatorial South America. Thank you for the Europeans for providing that. Then this just absurdly large 5-layer, it's the size of a tennis court, if you have a tennis court, has to fold out in all 5 layers and then stretch out. That did not work a few times in the laboratory when things were falling off. I mean, anyway, it had to work in space. One chance. That's it. Then, as you realize, it's a segmented mirror. It's not really useful unless all of the 18 hexagonal segments are in the exact same parabolic shape to a small fraction of a wavelength of light. Has to be a perfect parabola. That would be considered almost impossible to do. But that was one of the most, those are just some of the most expensive parts of the telescope. Now, the funny thing is, why did they have to do it this way? It's not just that they wanted to fold up the mirror. The mirror had to be much lighter, much thinner than Hubble Space Telescope. So you have a much larger mirror. It collects 7 times more light than Hubble, but it is the entire satellite, I think, is only a little bit more than half of the mass of Hubble Space Telescope. So that is amazing in itself. And then, of course, this telescope is designed to only operate close to absolute zero. It must be as cold as possible or it really doesn't work. And it takes a long time to cool off each of the parts of the telescope in a specific sequence until it can really begin to do any astronomy at all. So I guess you've seen these pictures. I don't know if it's, I'm not going to show you another launch. Gosh, you've seen enough rockets launching. This is kind of interesting, though, because there was, no, stop that. There was a camera on the top end of the rocket so that we can actually see the last humanity view of James Webb Space Telescope as it's going off into its distant orbit. Oh, shoot. I want to click. That's it. That's the top end of it right there.
And there is the view from the upper stage cabin on the Ariane 5 looking at the James Webb Space Telescope.
Still folded up,
It moves gently away from its launch vehicle.
There's a better view. Okay, so bye-bye Webb. That's the last anyone is ever going to see of you. But at least there was nothing broken at that point. All right, you already had this explained. You learned a little bit about Lagrange points, so I thought I would reinforce that. You want JWST, of course, needs to stay in fairly close contact with the Earth. So we really need it to go around once every 365.2 days around the sun. But we don't want it close to the Earth at all. That's a very bad environment for any kind of telescope, and it really wouldn't work. So this L2 point that you're familiar with, it's a marginally unstable orbit. If you get there, if you get exactly there, you will stay there for a while with the gravity of the sun plus the Earth basically balancing the centrifugal force, if you think about mechanics. But it's unstable, so you need to occasionally adjust yourself so that you don't wander away from this beautiful spot. That was a very big concern because once the JWST runs out of rocket fuel to maneuver itself, then it will lose its orbit. But the European launch was so perfect that it landed the telescope, it coasted right into the exact position it was supposed to be using essentially no rocket fuel. That's the main one of many reasons why this telescope in principle will be in operational position if the instruments are still working for 10 or 20 years in the future. If you think about it, that's another one of the reasons Hubble Space Telescope revolutionized all of astronomy. Not 1 year, it's the ability to follow up new discoveries that we don't even know what they are yet in this room. That's what's absolutely revolutionary. So the lifetime, very important. Okay, then of course, no data really could be taken for 6 months. The launch was on Christmas, but that was a great Christmas present, but we did not really get any data until the middle of last year. So I thought I would just give you some of my conclusions before, in case I forget to tell you the conclusions. But I have to stress, this is just a small example of some projects that I'm on, so I'm familiar with these particular results. But of course, every area of astronomy is being revolutionized, and I don't have time to talk about exoplanets, for example, which is amazing, and many other topics. So this is really very personal bias of what has been exciting to me to work on. I'm especially interested, as you know, in galaxies, and I especially like it when something that we thought that we knew turned out to be wrong. I like it when there's a surprise. That's a good way, actually, that science usually moves ahead. I can give you many examples from history. So, as we'll see, what you want to call a galaxy, if you go back close to the beginning of the universe, not too much after the Big Bang, these galaxies were converting a great deal of gas into a great deal of stars very early in very small regions, and doing a lot of other things too. For example, producing heavy elements, even the elements essential for life, carbon, nitrogen, oxygen, because none of those existed from the Big Bang. They could only be produced by the first stars in the first galaxies. And this has some other consequences too. Galaxies actually began to have disks, like a spiral galaxy. That was not what we thought. Galaxies, after they form heavy elements, this is going to be an important theme of my talk. Also, another thing that you can make out of heavy elements, if you have them, is interstellar dust grains. That turns out to be very important as well. They're good and they're bad, but we have to know about them. And of course, we can't really have a talk here without talking about quasars, can we really? Active galactic nuclei, that's another name for them, which tells you a little bit more about it. And I was really surprised at this, but it turns out nobody expected this. There appears to be a lot more of them just in our local neighborhood that we never had any idea existed. We completely missed them until JWST. So those are my conclusion. Let's see. So I guess if you heard any publicity about James Webb Space Telescope at all, you probably heard that it was supposed to study the birth of the first galaxies after the Big Bang. That was a selling point. But actually, if you talk to astronomers, the experts in this field, that's a very difficult project to do. In fact, I remember asking a number of people at a conference, I think it was a number of years before the launch. I don't want to tell you how many years the launch was delayed. You probably realize that it cost a great deal more time and money. Main reason for the delays, by the way, was NASA was scared about all those failures. So they just spent as much money. This is the most over-engineered telescope you can imagine. That's the main reason why it's so expensive. NASA could not afford another mistake like Hubble. They correctly realized the future of the space agency would be at risk if this mission has a failure, a very public failure. So, however, while we were waiting for this telescope to go, waiting and waiting and waiting, most of astronomers thought that Hubble would have James Webb would have a very difficult time to see the first galaxies. Maybe there would not be very much to see. They would be too small, for example. Maybe you couldn't really see the galaxies until they'd grown up to be something big at a fairly recent time. So a lot of people didn't think that we would see the early days of the universe because it was just too dark back then. We made a number of guesses. We took some bets. None of us won. Yeah, I was more optimistic than other people, but even I was not optimistic enough. Things turned out, the universe, I should say, turned out to be much more cooperative than any of us thought. So, in my opinion, already, I will say anyway, I appreciate the American taxpayers' help on this, and I hope that I think they are really getting their money's worth on this. We'll have to ask them to see if they agree. All right, so how are we, now I want to, hey, let's do a little bit of astronomy here, okay? I know not everybody's an astronomer here, so I get to spend a few minutes to remind you, review some basic principles of astronomy, and then you can appreciate more what JWST is doing. So how are we going to study the birth of galaxies? Well, there's one way that we have been using to do it. It's a classic way. We're using the well-known fact that compared to the size of the universe today, light travels very slow, only 300,000 kilometers per second. It's pathetically slow. And so any large telescope that has enough sensitivity, such as Hubble, in this picture you can see Hubble there, or JWST, if it can detect the light from very distant galaxies, it is not looking at those galaxies as they are today. We don't know what they're like today. Maybe they're like our galaxy. It is detecting the light that has been traveling from those galaxies for billions of years. It's a time machine. It is looking back at what the universe was. I guess you realize this. Billions of years ago. The bigger the telescope, the further we can go, the more powerful our time machine can take us back in time. So that's one fun thing about an astronomer. We have like a little bit of a Jurassic Park here, right? We can actually, okay, not that we're looking much further back than the dinosaurs. That was just yesterday. But we can go back and look at these young galaxies in their native habitat, see what they're doing. And the bigger the telescope, of course, we want to look far out in distance, because if we are looking far out in distance, because of the slow speed that light travels, we are looking back in time. So let's get a bigger look to see more galaxies further back. Move over Hubble, here comes JWST. That's almost to scale. Of course, the galaxies are not to scale on the picture, but that's the basic idea of what we're going to do. And it turns out that if you, all right, this is the tricky part. So you can look anywhere because the universe appears on large scales to be fairly uniform on the large scale. So it really doesn't matter where you look. You're going to find, if you look far enough back, you'll find galaxies way back in time. However, there'll be many, many galaxies in the foreground at earlier times, and then more galaxies even in front of those. So any place you look, you have a slice. It's kind of like archaeology. You take you drill a core sample. You start at the top of the most recent, and you drill all the way down a mile or so. We're going to drill through the universe here and look at recent galaxies, younger galaxies, and then galaxies back as far as we can go. That's the game plan when Hubble was launched. Okay, now we're using, so what is the difference between these distant galaxies and the foreground galaxies? I mean, you can't really tell so much just by looking at them. That's a classic problem in astronomy. We don't really have the third dimension. We just know the two sky dimensions, north, south, east, west of everything. The third dimension is a problem which astronomers have been struggling with basically since Galileo, right? One of our favorites there. But we have one fact that we must keep in mind, which I think was a surprise when it was discovered, but you know that. The universe, I should say the space itself, the space between galaxies has been expanding continually, steadily and rapidly since the Big Bang. So if I take any region of space, for example, the region of space between some interesting young galaxy and us, let's see, then it takes some time for the photons. I showed the photon that's emitted starts out here in my diagram as a blue photon, a fairly short wavelength photon. It starts traveling across the universe from this fascinating galaxy. It's traveling in all directions, but we happen to be in this direction. It's sending them out in all direction. And here's the point. As the photon travels across space, it's empty space. Because the space is expanding, the photon gets stretched. Its wavelength gets lengthened by the space around it. So in my drawing here, you can see that the universe got about 3 times bigger by the time the photon finally crossed this volume of space to reach the Earth, or above the Earth here, to be observed by Hubble. So even though it started out as a blue photon, by the time we emit it, it arrives as a red photon. Now, that's called the redshift. I will be referring to that a lot. People do get confused about that a lot. It looks really just the same as if this galaxy was moving away from us at a high speed because we're familiar with the Doppler shift. I find that somewhat misleading, but it looks the same as a Doppler shift. These galaxies aren't really going anywhere, actually, are they? We're not the most unpopular place in the universe that everybody wants to leave us. It's just that the space between the galaxies is expanding, and the photons expand with it. And I don't have a drawing of this, but if we're looking very far away, this space might expand much more than 3 times. Just over the traveling time of the photon, it might expand by 10 times or more, if we're looking really back close to the beginning. Of course, if you go right back to the beginning of the universe, all of the distances go down to 0. So the expansion from that time is almost infinite. We haven't really seen anything that's infinitely far back in time, but we're working on it. All right, here's how we're going to do this then. So this is the business end, the bottom of the telescope here where the light comes to focus. And so as you would do on a good observatory that wants flexibility and power, you have a suite of different instruments with slightly different capabilities, but they are all designed to be working at the long infrared wavelengths, because we already had an idea that that's where the new discoveries are. I already showed you one reason why, the high redshift. of the most interesting, youngest, distant galaxies means that we will pick up their light in the infrared. I'll give you some other reasons why it was important to build an infrared space telescope, something that Hubble Space Telescope cannot do. The main reason Hubble Space Telescope cannot do it is it's basically a spy satellite, and it operates at room temperature. And that produces so much of its own infrared radiation, you could never measure faint radiation from astronomical object. So there are the different cameras. They all work in the infrared, mid-infrared, near-infrared. And another important point about these cameras, they don't just take pretty pictures, although that was certainly a big concern at NASA headquarters. I must have pretty pictures. They have to be prettier than Hubble. I want these on the cover of every magazine, every screensaver, every newspaper. Okay, we got it. We got the biggest detectors that we can. More pixels means a prettier picture. But we also want to do a little more science with the data, and that means spreading the light out from a galaxy as a function of wavelength. So I hope you're familiar with that concept. You run all of the colors of the light. It looks like white light, but of course it's many different wavelengths combined, many colors combined. And for example, if you run the light through a prism, the blue light bends the most, the red light the least, and so you get a little rainbow spectrum. Well, that is exactly what most of these cameras can do on Hubble Space Telescope 2, except that they're working at infrared wavelengths to spread that light out that would not be visible to your eye. They are visible to these beautiful infrared detectors. These were somewhat developed for JWST. They're very useful for astronomers. They were originally, of course, for military application, night vision, things like that. But here it has a peaceful purpose also. So certainly would not have happened except for the military application. Okay, so our plan then is to do some of these core sample deep slices through the universe and look at the nearby galaxies, the medium far galaxies, the further galaxies, more distant galaxies, as far back as we can to the youngest galaxies, and piece together what has been the history of galaxies in the universe. So what we already were suspecting was that galaxies have changed a lot over the history, over the many billions of years, 13.7 billion year history of the universe. First, there were no galaxies, but then the first galaxies that started, very different from the Milky Way that we live in. We know a lot about the Milky Way, and we don't know so much about galaxies that might break the rules and be different. I'm going to show you some galaxies that really break the rules here. Galaxies that there's just nothing like them in our neighborhood today. First, before we talk about how little astronomy comes in here, if you want to understand how a galaxy evolves over cosmic history, over billions of years, well, a galaxy sort of defined to be a collection of mass which is converted gas into stars. So I think we're going to have to know a little bit about how stars evolve over time. It's interesting. Some stars take also billions of years to go through their lifetime. For example, the sun. Everybody knows the complete lifetime of the sun, that it can shine through thermonuclear fusion of hydrogen into helium. The total lifetime of the sun is approximately 10 billion. Okay, you get a t-shirt. Okay, that's correct. Right. Let's see. Solar system, we know very accurately, was formed how many years ago? About 4.57 billion years ago. Oh my gosh, is the sun about to die? Do we have to escape? Oh no. It's only halfway through its lifetime. So let's let other people worry about that problem. That's for the far future. That just shows you, of course, that some stars can live for a really long time. The stars I'm most interested, though, in, not because they're typical stars. The sun is a typical star. That's kind of what Copernicus would say. Nothing special over here, just a typical part of the galaxy. The stars I'm interested in are unusual because they're much more massive than the sun. There you don't, as as we learned this morning from Alan Stern, anything which is very massive is unusual. In the normal part of anything in nature is there are a lot of small things and relatively few large, massive things. It's true for galaxies, it's true for stars, it's true for atoms. I mean, it's true for everything that I can think of, including stars. But even though there are not very many massive stars, they are so powerful that when they are alive, they have a great influence on the galaxy. So they're of great interest to us. And when they're alive, we can see them much more easily than thousands of suns, which is not so easy to see. So here's don't worry about the stellar evolution. I put everything that you need to know about how stars evolve on one simple slide. Not too bad, huh? All right. So stars form from the original material of a galaxy. That's gas. Where does that come from? The Big Bang. And where did the gas in the Big Bang come from? We'll have to save that for the questions, because that's an interesting mystery, why there's any gas at all. But just assuming that gas was obviously produced in the Big Bang, when it starts to make stars, it makes all kinds of stars from stars like the sun, many more stars which are much smaller than the sun. That would be the most common kind of stars. Those are boring stars. And it makes a small number of very massive stars that might be 10 or 20 or 30 times the mass of the sun. So the sun is not special, but why am I interested in the massive stars? First of all, the massive stars, because they have more gravity, they have higher temperatures, they're basically very hot stars, so they produce high energy photons, blue light, especially ultraviolet light. The sun doesn't produce too much ultraviolet light because it's a small star. So I mentioned a few things about massive stars. I put it in italics here. Okay, I said that the sun lives a long time. It has a good hydrogen supply in the center, which can fuse, thermonuclear fusion, like a hydrogen bomb, can fuse into helium. The massive stars are doing the same thing, but they do it much faster. They're living fast and dying young. That's what the massive stars do. And so their lifetimes it's kind of ironic. They have so much fuel and they blow through it so fast. So they might live only a few millions of years, not billions of years like the sun, right? Thousands of times shorter lives. And so we're only going to see them during a short period after they were born, because they die fast. But boy, they do a lot during that time, because they have such a strong gravity, they are able to complete more advanced nuclear fusion reactions, to take helium and fuse that into carbon, to take carbon, fuse it into oxygen, oxygen into neon, into magnesium, into sulfur, silicon, and iron. So all of the elements that we're familiar with, including most of the essential elements for life, like oxygen, magnesium, and so on, are not produced by the Big Bang, of course. The Big Bang didn't produce anything except hydrogen and helium. They're not really produced by stars like the sun. They are only produced by these exceptional massive stars. So they're very important to me personally. And you'll see why in a second. You probably know this. Because those heavy elements that are essential to us, such as iron, it's in your bloodstream, can only be produced when those massive stars die spectacularly, as you probably know, in supernova explosions. That unlocks the heavy elements that were in their interior and gives it as a gift to outer space, to the rest of the universe, where it will someday end up in a new solar system, such as our solar system. Some of it ends up in new planets, such as our Earth. Some of those same elements end up in your body. As you probably realize, there's no question that the iron nuclei, the iron atoms in your hemoglobin that makes your blood carry oxygen, was in the center of a massive star. The star had to die first so that you could be alive. A little dramatic, but we don't mind a little bit of emotional appeal here. Even though we are scientists, we want to remain not too emotional, but I love that. So questions for for James Webb Space Telescope to answer about the evolution of galaxies. Well, our first question then is, when were they making stars? When were they making the first generation of stars? What did it look like? Well, I have some idea from when we see stars being born today. Here's an example in the Milky Way galaxy, a nearby one. I hope everybody recognizes this nebula. You could actually almost see this without a telescope. Looks like a little smudge on Orion's belt there. So that is a perfect example of recently formed stars of pretty high mass. All of that energy, this is I don't know, 10 light years. It's a big region. Anyway, all of the power is being generated by, well, you can see them. Those 4 stars there, pretty much doing everything, but they're massive. So it doesn't take a lot of stars. But the thing that you notice the most about this is it's surrounded by the gas cloud from which the stars originally formed. That's the birth grounds of the stars. And so as soon as they're born, then they heat up the gas cloud out of which they formed. Any idea why? What color do you notice there? Looks kind of red or pink. That's the true color, what you see in a lens of a telescope. One of the problems with a lot of the Hubble pictures, people are used to extreme digital manipulation of pictures to make false color. And they're always disappointed when they look through a telescope. But actually, that's what Orion pretty much looks like. That is a very characteristic emission line. Oh, we're going to learn what those are from the most common element in the universe, which is the simplest element, which is, okay, you have to give him your shirt. It's hydrogen. Neon is not uncommon, and it has some interesting properties. I think you're just messing with me. Okay, so thank you. All right, but he is paying attention. All right, so that's going to be useful because we have a chance to see a group of young stars like this, even at high distances. There's a galaxy, well, that's a nearby galaxy, which has hundreds of Orion nebulae forming their gas clouds, which have been heated up by young massive stars, which have not died yet. They're going to die soon, but while they're still living, they give you beautiful light shows. See these spiral arms? That's pretty much what a spiral arm is in a spiral galaxy. You see all of these young stars making these pink glowing regions. Each one of these is maybe 10 Orions or more, and there's dozens or hundreds of them around there. So maybe that might be what a young galaxy would look like when it first formed. But, okay, first of all, they're going to be thousands of times further away, so we're going to need incredibly high magnification to study them. They'll be very faint. We'll need a huge telescope. Well, all of this will be redshifted to infrared wavelengths, and then we may find that things are quite different from this. In some ways they're similar, in some ways they're different. I'll show you. Anyway, that remains for me to show you. All right. Now here we get the astrophysics part. Okay, I'm sure you enjoy this part. A little bit of physics here. It gives me a chance. So how does it work? I mean, I showed you what's happening, but now I want to explain what's happening. All right. What's happening here is that we have hydrogen atoms and other atoms, and they are hot. So, as you know, a hydrogen atom has how many electrons? It's the simplest element in the periodic table. 1 proton, 1 electron. So this electron you might usually expect to find it in its lowest energy orbit, close to the proton. That's where it would settle down, because everything in the universe likes to settle down to its lowest energy level. Even people do. But because this is a hot gas, the electron will often find itself in a higher energy level. And then what's it going to do? It will wait around there for a little while about 100 millionth of a second. That's a fairly long time if you're an atom. And then it wants to drop back down, but we must conserve energy here. If it's giving up this much energy from a high energy orbit to a low energy orbit, remember, that's the key insight of quantum mechanics, that the electron can only be on certain steps of a staircase. It's quantized. It cannot be in between. So it will drop down here, giving a precise amount of energy to what? Where's that energy going to go? A photon, you've got it. Okay, you can have your shirt back. So the photon, of course, core is a packet of pure energy, right? It's a combination of electric and magnetic vibrations. And as you probably know, if you measure the frequency of the photon in cycles per second, then you multiply that times a very small constant of nature, the Planck constant. That tells you how much energy the photon has. It's a specific frequency corresponding to the electron energy levels of that atom. It's a fingerprint that's distinct because one frequency means one particular color of the rainbow here. And so in particular, hydrogen, when it drops from the third orbit to the second orbit, it gives off a pink photon that you saw. It's a very common thing for it to do. If it drops from the fourth energy level to the second, it gives off sort of a blue-green one, and other energy levels, it gives off these other photons. It's just like a fingerprint there. And you see what we're looking for. It's an emission line spectrum. This is, the light is spread out like through a prism. Here's the violet, here's the red. There's nothing in between. This is quantum mechanics. Only these very bright features at specific wavelengths. That sounds nice for observers. Something, when we spread the light out, we can really notice these emission lines very easily. Sounds good. What about the supernovas? We are also in I just don't only want to know about how stars are formed, I want to know about how stars die, massive stars. And, well, I already told you the answer here. When these massive stars die, they're going to produce supernovas, and the supernovas are the main supplier of all the heavy elements in our galaxy today that we depend on, for example, for the seeds of life. So this is really just a shameless plug here because, of course, a number of other speakers had a lot of things to plug. They're very famous and so on. All I have that I can try to market here is just this one little book. So, and this is just the cover of the book. But the cover of the book does have a nice supernova on it. So I thought I could put it in the slide here, and maybe a few more people, in addition to the few hundred people, I don't know, maybe it's 1,000 people, whatever, who have bought this book already, will buy it. It covers a lot of these interesting things that I'm saying before the James Webb Space Telescope. It covers up to Hubble Space Telescope. I hope this book is not completely out of date, at least for another year or two. Maybe we'll get a contract to do a third edition. But what else was I going to say about that? Well, there it is. Oh, no. I don't know the English version. I don't know what it's going to do. Americans don't really read science books. We are selling a lot of copies, though, from a Japanese translation, because they read a lot. They love astronomy. So, I mean, the only place I've ever seen this book anywhere is whenever I go into any Japanese bookstore. Anyway, yeah, great. I'm sure you're very interested in that. Okay, so one last review now. Okay, so now we know what's in galaxies. They have stars of different temperatures, and that is they're just producing starlight, which is just a continuous. Whoop, yeah. Well, there it is, right there. I'm showing you just a continuous range of emission from the violet to the red. That's what the stars produce. But if the galaxy has some recently formed new stars, then we can see those Orion nebulae also producing a little bit of a contribution to the spectrum of the galaxy. And so if we're lucky, if there are some young stars there, we may see, do you see that? You can't miss this, right? Even if you're in the back there, You see the difference of the top galaxy? At certain particular wavelengths, the galaxy is much brighter because of those distinctive fingerprints of atomic emission lines. And we know what these lines are because they're at the same colors that you can measure in a laboratory on Earth. Right? It's a very powerful thing, of course. It's the unity of science, right? Hydrogen atoms, oxygen atoms, 10 billion years away, they're the same as oxygen and hydrogen atoms we measure here. Absolutely the same. Everything about them the same. Same laws of physics, same speed of light, same Planck constant. Otherwise, I think it would be almost impossible to do science. So, a little philosophy there. All right, so we want to look we want to spread the light out of these galaxies, see what we're going to see. Okay, that was a long introduction. Now I finally get to show you some James Webb Space Telescope data. Oh, by the way, I thought it would be fun to put a little label on what atom causes each of these particular colors here. Hydrogen, oxygen, sulfur. Okay, interesting. Oh no, I have one more. Okay, I have one more trick here. I'll just make this quick. This is the opposite effect of an emission line, and this turns out to be very useful. So let's go back to the hydrogen atom one more time. Last time we're going to worry about the hydrogen atom. This is the last quantum mechanics here. So here again is the ground state. This is the lowest energy that the electron can be in. It's very close to the proton. If it picks up a large amount of energy, energy is going up here. If it goes above the escape energy, shown by the dashed line, I wonder how the electron could pick up such a large energy. If it could get such a large energy, what happens to that electron? It escapes. It's gone. It's free. It just leaves behind an ion. It's ionized. But that's a long way. That's a lot of energy to come up. How could a hydrogen atom receive so much energy? It would correspond to a very high frequency photon, because a photon has an energy equal to h times the frequency. Well, if frequency is really high, far into the ultraviolet, then that energy, the energy of one photon would be enough to liberate an electron. But at what cost? It's the opposite of the emission line slide. I'm sure you just remembered that one. In the emission line slide, the electron gave up energy, and what was the result? The energy created a photon out of nothing, out of energy. What's going to happen now when the energy is taken? The photon will come in, give the energy to the electron. Fly, electron, fly away. What's going to happen to the photon? It's destroyed to balance the books, conserve the energy. So here's what happened. There goes the high frequency photon. I made it ultraviolet here. It comes in, and then boom. In the next second, the electron has escaped, and now this photon is gone. So now I've shown you how hydrogen could lead to absorption. I wonder why that's important. And why am I so fixated on hydrogen? Because hydrogen is by far the most common atom in the entire universe. Most galaxies are going to have hydrogen in them and all around them. And a lot of the hydrogen will be in this ground state here. So it's very dangerous for high frequency, short wavelength, ultraviolet photons to travel around the universe, because they will probably pretty soon run into a neutral hydrogen atom, which will destroy them. So this is such a common effect that you could be pretty confident that the highest frequency photons, or I should say the bluest, or the shortest wavelength photons, will not be able to escape from a galaxy. Could we use that? This is a trick. Yes, we could use that to discover galaxies that have this absorption. We know what the wavelength is. It's about 1/10 of a micron. That's pretty far on the ultraviolet. So here's the plan. We'll look for galaxies which we'll just take images of them because that's simple, through a few different wide color filters. And then we'll look for galaxies which are become invisible in the shortest wavelength. Then we'll and that's perhaps because neutral hydrogen has absorbed all the shorter wavelengths. Then we see which is the wavelength where the galaxy dropped out. That must correspond to this wavelength of hydrogen. So let's see. I think I want to switch now and go to a movie. Can I do that here? All right. No, I have to stop this, I think. And show. This is where the technical stuff comes in. Let's see. Can you see that? Okay. So forget the other movies here. What we're going to do is we're going, well, it says right here, we're going to, this is a simulation, but quite realistic. We're going to take a series of photographs. Hubble did this, actually. You can do this with Subaru telescope or a lot of telescope. Take really nice photographs, red, green, orange, yellow, blue, violet, and so on, and look for any object there. It's a needle in a haystack. We're looking for very distant galaxies, but we have no idea which ones are really distant unless they disappear in the short wavelength images. They're called a dropout there. They just go away. That would be an indication of a galaxy where we're seeing the hydrogen absorption, and if we see it, think about this, if we see it's supposed to be in the far ultraviolet. But if we detect this absorption in the optical, that's because it's a very highly redshifted galaxy that must be very far away. So here's how this is going to work. I'm sorry there's no music for this. Maybe I send these guys some music. They're pretty good friends. Okay, so the higher the redshift, the more the wavelengths are stretched. Okay, so you see that? Here, well, it's just, they're sort of selling it. Okay, so here is a blue filter, red filter, far red filters. These are pictures that Hubble Space Telescope could take of a sort of a weird-looking galaxy here. And this is a spectrum of the light that comes from a bunch of stars in a distant galaxy. No far ultraviolet light can escape. So as we look, suppose this galaxy could be put further and further away at a higher and higher redshift, then it will simply disappear in the shorter wavelengths here. Let's see if this thing, there we go. Higher redshift, there it goes. Now it's a blue dropout, a red dropout, an infrared dropout, right? Now it's almost a total dropout. One of the things that's a little scary here, by the time you get to really high redshifts, oh, we don't have to give those guys credit. By the time you get to really high redshifts, this galaxy might be almost invisible except in the infrared. I don't really want to study a galaxy where it's only detected in one picture. That really scares me. In fact, that scared a lot of people. But JWST could detect it in several infrared pictures. So where was I here? My gosh, that was the introduction to this talk. I'm really sorry it took so long. Hope we have a little bit of time for question here. I never gave this talk before, as you can tell. So that's what we're doing here. All right, we're looking for hydrogen absorption at a large distance. We found it. This is spectacular. This is a spectrum of a random galaxy. We already knew that this galaxy could not be seen at visible wavelengths already. And so that was a hint that it might be interesting to look at. And sure enough, when we look in detail, can we confirm that this really is at a very high redshift? This is the way to prove it beyond a reasonable doubt, right? This is when we had a suspect. The galaxy was suspected of being at high redshift. Now we have the proof this galaxy is convicted. It goes to jail. We definitely know why. Look at this beautiful spectrum here. It's detected. This is starlight from the galaxy. All of a sudden, these photons here have a higher frequency. They're more to the blue, short of 1 micron, and they are all, every one of them, absorbed by neutral hydrogen, except corresponding to an amazing redshift. It's corresponding to a galaxy where the wavelengths of all the light have traveled so long, the universe has expanded by a factor of 9.31 times as it traveled to James Webb Space Telescope in every dimension. So the universe, when this galaxy is being observed, was what? I don't know, almost 1,000 times as denser and smaller than it is today. So that's pretty impressive. And I would mention another thing that's impressive about it also. I mean, when I saw this, you just have a lot of emotional reactions when you see this. You also notice, of course, there are emission lines, as we expected, much stronger than what you get in Orion Nebula. This whole galaxy has lots and lots of young stars and hot gas, including some heavy elements already. Here is oxygen. Remember, I had a little O there. This is oxygen also. So this galaxy, even though less than 1 billion years after the Big Bang, so the universe, was only 6 or 7% of its current age, already some supernovas had produced heavy elements. And I show you some of them there. So that was a wonderful discovery. It shows that this whole program that I described, it took quite a few minutes to tell you this program. This program is going to work. So we now have a way to, we're looking through all of these galaxies, and we can pick out the ones that are the most distant, closest to the Big Bang. It's going to work. Now I'm going to blow your mind here. Takes a while to explain this one. We're going to use the same method. You already know the method. This, we're using another trick to help us go even further. I think this was described in an earlier lecture. We're using the magnifying power of large gravity from big mass to bend, deflect, focus together light from a distant background object. What's the large mass in the upper picture? This is one of the largest concentrations of mass in the local nearby universe. It's a cluster of galaxies. Every one of these is a very massive galaxy. So it's an enormous amount of gravity there. And by coincidence, of course, behind that cluster of galaxies, you can find some other little objects. Normally, we would not pay any attention to these objects, except that their light happens to pass close to the mass. So even the light that it was originally going in different directions comes together to our telescope. I mean, that's basically how eyeglasses work too, to bring the light from different directions to the same focus. Well, this is gravity making a powerful pair of eyeglasses. This little object right here is 13 times bigger and brighter than it would be with no gravity. So I love this. We have JWST, which is already a high magnification telescope, combined with the additional natural magnification of gravity, and it's an incredible combination here. So there's also another image of this galaxy, right? You can get more than one image from these lenses, just like with actual glass lenses. There's even another image of the galaxy here. Anyway, whatever. For various reasons, our team decided this was this interesting object, and we decided let's take that object, and I don't know, 40 or 50 other objects around here that we thought might be interesting, maybe hydrogen dropout objects. Let's put the light into our spectrograph, spread it out, and get an actual spectrum of it. And here's the spectrum down here. And you might be thinking, well, that's pretty noisy. Yeah, of course it's pretty noisy. We're not using JWST to do something that's easy. But again, you can see that even at a longer wavelength here, it's about 1.3 microns. As we had suspected, the light goes away. It's coming along. Okay, it's noisy, but it's detected, and it suddenly goes away from the hydrogen absorption. Now this also we were able to confirm some hydrogen emission lines. So that's a pretty high redshift. Now, at that point, the universe was 11 times smaller in each dimension when the light from this object came to us. Here's the interesting part. So far you're going, okay, that's great. You guys are just keep on going. Just go to higher redshifts. You can have a competition. Who can get in the Guinness Book of World Records? Most distant object. I don't care about the Guinness Book of World Record here. Look at this object. Yep, look at this object. Remember, this is highly magnified. It's so small. That's a big point I want to make here. Some of these objects are forming a lot of stars in such a small region. It's only half of the light here, we estimate, is contained within just 100 light years. Within just 100 light years of the sun is almost nothing, right? I don't know, a few thousand stars or something. Milky Way, of course, is 100,000 light years across, right? So this is too small to satisfy any conventional definition of a galaxy. Until we took this data, my definition is that this is just a star cluster, right? Really, just a big cluster of stars. But apparently that's what the first galaxies were. Very intense, concentrated bursts of turning gas into stars. I think we really are going to have to go back to textbooks and change what do you define as a galaxy? What do you define as a cluster of stars? Because previous definitions really don't work. This is a rules breaker, and I don't think there's anything special about this object. We were just lucky to have the magnification to be able to observe it. We could do more of these. Okay, so this method, okay, Lyman break, it's an ultraviolet, it's a dropout method, works pretty well. Okay, I go through this pretty quickly. Wouldn't it be nice, though, to have emission lines? Remember, those are really bright, brightening in the spectrum. The problem is, if you go back and look at the previous spectrum here, this is where we have the most sensitive observations here. No emission lines. It's just unfortunate trick of nature that there aren't much emission lines in the region that we're usually going to get to observe. It's very difficult to observe at such a long wavelength there. Except there is one possibility. There is one emission line that we could look for from, well, what would be the strongest emission line? It should come from hydrogen. This is the strongest emission line that hydrogen produces. The problem is we did not expect to see this emission line because for basically the same reason that these galaxies are a dropout. We were afraid that this emission line is too easily absorbed by neutral hydrogen. So we actually discussed this a great deal and predicted that if there is any neutral hydrogen around at all, this isn't going to work. This is our ticket to find the most distant youngest galaxies, but the ticket is not going to work. That's what most of me and my friends said. In fact, we published some papers on this using Subaru data. We can't go back above a redshift of 7 or 8. There's just no escaping of these beautiful Lyman hydrogen emission lines. Okay, and the reason for this is that if you go back in time, which is what this diagram, this is our last educational diagram. Here is the time close to the Big Bang. As soon as the universe cooled down, it was filled with neutral hydrogen everywhere. Very difficult for those photons to go anywhere. So here's a Lyman alpha photon that's emitted. It travels a little bit. It gets killed. It's absorbed by neutral hydrogen. More recently, when the universe became hotter again, most of the hydrogen has become ionized, so it's called H2. That's ionized hydrogen. Ionized hydrogen is no problem. It doesn't absorb anything. So we can see galaxies emitting these lines only if they're in the modern ionized part of the universe. This is where we are. This is where Hubble and JW are today. However, we might get lucky, perhaps. What if we could find a galaxy that was in an early ionized bubble of gas? By the way, that raises the question, what caused all of the hydrogen in the universe, which was neutral, what caused it to all be ionized today? That's correct. Let's now for the two-pointer question here. Where did that radiation come from? That's right. Ultraviolet radiation from the first generations of stars. Okay, you get a second T-shirt there. All right. So the first generation of galaxies, if it started early, would make some escape channels where we have a chance, maybe, to see these emission lines traveling from very high redshifts. But nobody yeah, that's a bunch of theory. Nobody, it's models, it could be all wrong. Nobody really expected to see this. Oh my gosh, I remember when I first saw this thing, just a pathetic little faint object. Of course, the starlight is detected on the long wavelengths, nothing detected on the short wavelengths. But before the absorption sets in, do you see the emission line? Due to a lot of hot hydrogen? Well, if you don't see the emission line, I don't want you to miss it. There it is, at a very high redshift, almost 11. It was already suspected that it might be a galaxy, so that's what already broke all the records compared to what most of my friends were expecting. And, you know, everything I'm showing you here, the universe could have been the way we thought, or it turns out to be easier for astronomers. Everything I'm showing you basically is sort of a lucky break in our favor. I love it when nature turns out that way. It wasn't at all guaranteed. Now, a few more minutes and then I want to wrap it up. So I told you that we have to worry also not just about the gas in galaxies, but a small fraction, less than 1% of the gas in galaxies is in the form of interstellar grains. They're very small, but they have a tremendous effect on light waves. And you already have seen this, right? Everybody knows about interstellar dust, even without a telescope. There's a view of what? Milky Way galaxy at night. There's the center of it from the southern hemisphere. There's our two nearby neighbor galaxies, the Magellanic Clouds. You can't even see the center of the Milky Way galaxy in Sagittarius. It's completely absorbed. All the visible light doesn't get through the absorption of interstellar dust. A terrible problem. Crippling problem for astronomy. We've been struggling with this as soon as it was realized, 70 years ago. What's the solution? These dust grains are very, very small. So a short wavelength photon will be absorbed and destroyed. A long wavelength photon, you know this, of course, with long wavelength radiation, radio waves and so on, can go around obstacles. As long as the obstacle is smaller than the wavelength of light, the light can travel through. That's exactly what you see in the universe. So I'm going to show you exact same region of the Milky Way galaxy. There's the plane of the Milky Way galaxy, except instead of showing you an optical picture, I'm going to show you an infrared picture. And now you'll see almost everything coming through. Same region, aha. Now, not so much is absorbed, you see where everything is. That's another reason, not just the high redshift of young galaxies, but also the fact we need to see through this interstellar dust. We need an infrared telescope. Hubble cannot do the job, aside from being too small. Just, I don't know, Winston said I should put a slide to explain this, so, back to school for one more minute here. Here is a little model of an interstellar grain, greatly magnified. You see, it's about the size of an ultraviolet photon. So these ultraviolet and blue photons tried to go through, and they're just very easily absorbed. They cannot pass. The longer wavelength photons are fairly big in wavelength, so they see this as a small obstacle, and they can bend around it, or they just go straight around it. So they don't get absorbed. Now, I don't know if you like this cartoon or not, but so it's a fact, an inescapable fact, that as soon as the universe produced heavy elements, these are made of heavy elements, carbon, nitrogen, oxygen, silicon, magnesium, and so on. So as soon as the first supernovas produce heavy elements, there is a possibility that galaxies are going to start forming dust grains, and they're going to begin to get obscured, just like the Milky Way. And in this cartoon, you have a person whose job it is to clean dust away. Okay? So she's a cleaning person who likes to take dust away. And they're looking at the stars in the sky, and one of the cleaning ladies says, "That's really very beautiful." But the other cleaning lady is probably right. There's so much interstellar dust out there, it makes me feel very bad. She's, of course, exactly correct. But, okay, all right. You would not really know about this if you just use Hubble Space Telescope observations, because Hubble Space Telescope observations are limited only to short wavelengths. So basically, Hubble told us about galaxies which don't have much dust in them. Those are the only ones that it can detect with its cameras. It's like looking through the center of the Milky Way. There's only a few regions accessible to Hubble. And over the years, people started to think that that's normal because it's what we're used to from Hubble, but we were wrong. Here's an example. Hubble, kind of complicated. Here are galaxies at a number of different redshifts, up to fairly high redshifts. Hubble said that all of these galaxies, as you go back in time, are strange looking. The technical scientific term is peculiar or irregular. It means we can't classify them. They don't look like spiral galaxies. They don't look like the Milky Way. They don't have those nice little disks in them. But that was wrong. That was a mistake that Hubble made because it's not really seeing through the dust. It's like the first picture I showed you, the optical picture, instead of using the infrared picture where you could see where the galaxy really is. Anyway, JW, in this paper we did, finds lots of disks actually early on. So it was just, they were missed by Hubble Space Telescope. This is what's happening, just to show you here. Here is what Hubble Space Telescope would see in these distant galaxies because it's measuring optical light which started in the ultraviolet. And I will admit those galaxies look pretty bad, right? They really don't look like anything. So you can't really classify them. But that's Hubble. Now, James Webb Space Telescope, since it's observing in the infrared, with the redshift, these are distant galaxies, we're actually getting views of galaxies comparable to what we've had for many years in local galaxies. And now you can tell what they are. Spiral galaxies. Anyway, so that's just a morphological result that I thought was cute. Other result, okay? I'm going to skip through this pretty quick. This was one of the first discoveries of large amounts of dust emission in high redshift galaxies. And again, you didn't even realize it was a problem, probably because you're not working in the field. But the Hubble Space Telescope, conventional wisdom was that there shouldn't be such galaxies that have so much. This is entirely the glow of heated dust grains here. Anyway, all right. Why is this galaxy a ring, by the way? Any guess here? Gravitational lensing, you got it there, very good. I guess I've been reading the slide. There's a massive galaxy in the front here. Right behind it, it's like a bullseye. Right behind it is a little galaxy which is so magnified that it makes a so-called Einstein ring. So this is the distant galaxy here. And it actually has a lot of dust in it. This is kind of a surprise to me. We also studied this galaxy. It's the same galaxy here. It has a lot of heavy elements. I mean, I was expecting maybe a little heavy elements because there hasn't been much time for many stars to die. But apparently, if we're right about this, so many stars were born, so many stars evolved, so many stars died, so many stars have supernovaed, that this galaxy has about the same amount of heavy elements as our galaxy. It's similar to the composition of the sun, you know, a modern star. That really surprised me. I mean, galaxies apparently were making these heavy elements much faster in much larger quantities than anybody suspected. Kind of a mystery. You know, I love this project, but I think I'm going to skip it. Okay, this is my wonderful project. It has a great acronym, love it. But anyway, the only point of this project, which is the largest Cycle 1 project on Hubble Space Telescope, I'm a principal investigator of this one, is it allows us to take spectra of lots of thousands, tens of thousands of galaxies, not just a few dozen galaxies, with no selection. So our program is taking a spectrum of anything that everybody else ignores. That's interesting because everybody else might have missed something. What they miss is some galaxies with incredibly strong, ridiculously strong emission lines in the infrared. Doesn't look very impressive at all, very small, but it's just a big cloud of gas forming stars at a crazy rate, a burst of star formation. Anyway, those are the oxygen and the hydrogen emission lines, and anyway, it kind of changes my idea of what a galaxy is, and you never would know about these before. I had another example of this here. It's like a pure ball of hot hydrogen. I don't know. It's like looking at just the Orion Nebula if you took away the heavy elements. Quite amazing. All right. Finally, I got it. Do you think I should just stop here so we can do questions then and skip the quasar part? Up to you. Do you want to see the quasars? He likes quasars. Okay. One last question that we want to know about how galaxies evolve is, what about the giant black holes in the centers of these galaxies? There's an artist's conception of one of the black holes in the center of the galaxy. Guess where that is? When it has a source of fuel, gas spirals down onto the black hole. Because of the enormous gravity of the black hole, the gas gets so hot that it radiates enormous energy. It's a much higher efficiency of extracting energy from fuel than fusion power is. This is a gravity power. And so we know about these objects, and they are so powerful that when they're shining, they might change the history of their galaxy. Interesting question. All right, so that's an artist's conception. Let's rotate it around to straighten it out. In the next picture, here's the question. This is a complicated schematic diagram. If you could look into a galaxy that has a giant black hole in the center of it, this is a logarithmic scale, basically in light years here. The black hole is, the size of the solar system. So that's pretty impressive, but it's tiny compared to the galaxy. Here is the very hot gas that's spiraling around it. And basically, I would say the reason that we know about that hot gas there and how this process works, the central engine of quasars, is primarily because of Wei Xin's PhD thesis. His dissertation measured this really for the first time, determined the size of this, the mass of the holes, and a number of other interesting facts. Okay, so that's how you could find quasars. Just look for all of the heat and radiation coming from around the black hole. That's easy. Here's my question for today, though. What if it's like the Milky Way, we don't have a direct view of the center? What if it's been blocked? Well, what could block our view? What blocks our view to the center of our galaxy, where there is a black hole? We don't have a direct view of it. Interstellar dust. Well, we know that there's interstellar dust around quasars. Also, this is a schematic. It's shown by these little red blobs. We don't really know exactly where this interstellar dust is. This is just a guess here, a bunch of interstellar dust grains. And you see the problem. Depending on whether you're lucky or not lucky, you might have a clear view of the quasar, or you might have a totally blocked view of the quasar. There's a totally blocked view of the quasar, right? If we're over here, we don't really know where all of that, we can't see all of this energy that's being produced. We could study it if we were looking in from here or looking in from another angle. It would be a traditional quasar. Basically, Wei Xin's thesis, it's all traditional quasars. Okay, we wanted to avoid this problem. However, we wouldn't know about it. There's only one way that we would know that so much power, so much gravity power is being released in such a small region. How would we know that? Conservation of energy. All of that, it's this ultraviolet X-ray energy. It all gets absorbed by these dust grains, which are maybe a few light years out, maybe 10 light years out, and they get very hot. In fact, they get so hot that they barely can survive. 800 degrees Kelvin, that is really hot, right? You think most things evaporate at that temperature, right? It's almost as hot as a light bulb, okay? So what happens when you have a solid object that's very hot? What kind of radiation does it produce? Infrared light, that's correct. Okay, well, it says on here, that's right, so-called black body radiation. So we now have a new way of finding that there is a buried, hidden power source in the center of a galaxy that you otherwise wouldn't know about if you can study it with very high magnification in the infrared. And the only telescope that could ever do that is JWST. I just ripped through this really quickly. Here are two galaxies in a collision. Hubble Space Telescope had no idea what's going on. Here's the central region where the collision has happened, and you just see, even in the longest wavelength channels that Hubble could use, you just see a few things that look like little clusters of stars. So everybody, including me, every astronomer, assumed that these are just stars forming in this galaxy. There's nothing to look at here. As soon as we saw the James Webb Space Telescope picture, we realized we'd missed something completely. You'd never pick this out. Sort of like the fifth, this insignificant object. See this thing? It's called D1. Like, who cares about D1? It's like nothing here. Oh my gosh. D1, when you look at the long wavelengths where you could see the thermal emission, is putting out all of the energy of this entire system. This, we believe, we interpret this, and John Way and I have been going back and forth on this because he discovered and studies objects like this too. We're thinking this probably is a quasar, an accreting black hole that can only be seen through its infrared emission, and there's more of them. I mean, if it was just one weird object, they're all over the place. This is shocking me. This is another one, completely invisible to Hubble. Hubble can't see anything over here in this galaxy. But as soon as JWST looked at it, we said, my goodness, look where all the energy is coming from. This one little invisible spot is producing all of this heat energy, and we didn't even realize it. I remember I was so surprised when this happened. Fortunately, this is preserved for posterity in history because there was a television crew filming a documentary for the National Public Broadcasting Service in Pasadena. And so I saw the data, and oh, by the way, you can tell that that's me, right? Only person in the room with the official JWST jewelry here. You can come and look at it later. Obviously me, and pretty much here's a direct quote. When I saw those data, I wasn't thinking, you know, about that there was a camera or something going on. I just had an immediate emotional reaction. Holy, that's a new AGN. Well, you can't really say that on television anyway. So this is the scene in the final documentary, but there's no audio there, so you don't really know what I'm saying. Anyway, but that's okay. It was really a lot of fun. So my conclusions here are just a few personal discoveries that were completely unexpected, and there's so many more in different studies of astronomy. Here's my big conclusion. This is an incredible time to be in astronomy. You guys, if you want to be astronomers, are like almost the luckiest people in history, practically, pretty much, to have these tools available. And if anybody asked me a question, I could show you what the next tool is that's going to make more revolutionary advances following up on JWST. But here's my big prediction. I showed you some discoveries. What are going to be the biggest discoveries of James Webb Space Telescope? This is guaranteed. This is absolutely solid. Because every time you have such an enormous advance, let's say 2 orders of magnitude improvement in sensitivity and wavelength coverage and resolution and so on, what is the biggest discovery that you find? It's the discoveries that you had no idea what they were because you didn't even know which questions to ask. They were not predicted. That's true of all of the big Hubble discoveries. They were not predicted. I wrote some of the documents. What is Hubble going to find? What should we be studying? What is the future plans for Hubble? Those were all wrong. All of the biggest discoveries were not in those books. Could not be predicted. That's going to be true with JWST also. And that's a prediction that I will stand behind. You can take it to the bank and guarantee it. I just don't know what those discoveries are yet. Thank you for listening. Let's have some good questions.
Okay, well, thanks very much, Matt. It's a great and very inspiring talk.
went kind of long.
Yeah, especially the part about my PhD thesis.
Well, you see, that was the key to the whole talk, pretty much.
Just kidding. Well, there's one point that I was very much impressed is when I was in a class teaching general astronomy and talking about Keck, two Keck telescopes, Mauna Kea and Hawaii. And it says down there, the 4 major discoveries so far done by Keck telescope were never in the proposal.
Correct. That's correct.
Yeah. 就是大家知道，就最重要的4个发现，在原来申请经费盖的望远镜的书里面完全没提到。意思是说，你做一个新的仪器，你根本不知道你会发现什么东西。That's strange that you don't know what you're going to discover with the new instruments, and those guys still give you money to do it.
That's why I like astronomy. It depends your personality and temperament. Maybe you don't like so much uncertainty. You want to have some more solid data. Then you can work in a certain area of chemistry or something where you're trying to get a precision answer. I'm not a kind of a precision guy, I'll tell you. So I like a wide open territory where it's a wild west. Nothing is known at all. Almost anything is new, right? And so all of the big experiments pretty much that got the Nobel Prize in astronomy were serendipitous accidents. Every single one of them was not planned. But you notice how the accidents always happen? They always happen to the person who has the new, more sensitive, far superior way of looking at something that nobody else could do before. It's not an accident, is it?
No.
Really. And exactly the same thing is going to keep happening here.
We want them to learn a new English word. 有多少人知道刚刚Matt讲那个是 serendipitous？ 知道的请举手。
What is that in Chinese? They don't know. Serendipity. Science. Serendipity.
无意间的，就是你很多时候你根本不知道但是你要注意，刚刚Matt讲说你要观察，很多东西出现在那个地方，你没有观察能力就错过了，你有观察能力就注意到别人没有看到的东西。That's what's called discovery. OK， 有没有问题要问Matt？OK， 你讲太多先。
Hello, Professor. I have one question. It's about the redshift. You said we have the cosmic redshift, but I want to know how can we distinguish the redshift is the cosmic redshift or the Doppler effect of light redshift, because it will cause a different solution. The solution.
Yeah. Well, what can I say? So you're questioning the cosmological nature. Are the redshifts really measuring an expanding universe? I can't.
你说的是宇宙红移跟 Doppler shift 打的是？那它的都普勒红移。Yeah, Matt. So you do get the question.
I can't give you a good answer. Part of the problem is that the best measurements of the expanding universe and the cosmic distance and time scale, which is the basis of the expanding universe, some of the most important papers on that, first author is my wife, so I can't really insult it too much. But let me just be honest. There is such an incredible pile of different kind of observations, the microwave background, which I didn't discuss and so on, which does not have any other explanation unless we actually are in an expanding universe that started in a hot, dense state in a Big Bang. If there, of course, were a number of theories around, a steady state theory and so on, that was killed by the discovery of microwave background. If you want to have a new theory now, you have to explain an incredible number of consistent observations with your new theory, and then have a new observation that only your theory can predict and the other one doesn't. In other words, as Carl Sagan said, if you want to make an extraordinary claim, you have to have extraordinary evidence, and there's nothing like that at the moment. So I'm open. I've seen a few huge mistakes astronomers made, but I have not. But I think it would be incredible if the expanding universe starting with something like a Big Bang is not approximately true.
Matt, talking about the mistakes, I want to mention one thing is that in one of these conferences, when the Hubble Space Telescope was fixed, was that CoStar machine, and Hubble was able to gain its original design capability to do very nice observation. And then in that meeting, people noticed that it was a mistake made before, published papers, many papers, on the wrong interpretation of an object. That's the exploding star. You remember that one? And
you mean the supernova paper?
Not supernova, but a late-stage star. Just
well, mistakes happen all the time, and we should be aware of the possibility. But you're asking for a really big mistake. Anyway.
Yeah, and in that meeting, people were kind of embarrassed and afraid not to say anything because there are so many PhD theses.
Here's the problem with science. The problem with science is when our human motivations, ego, and so on, gets in the way of the evidence and the truth. Right? That's the reason for inventing the scientific method. It's so that we can try to get to the best description of the data without being biased by, oh, my thesis advisor, my whole research team believes this. We published so many results here, now it's going to be destroyed. Right? Well, I'm sorry, but scientific method is to protect us against those biases.
Yeah. OK， 好，所以其中还有讲，我短一点时间好不好
？You certainly have earned a question, sir, because you gave so many answers here.
好，简单的那个。
Okay, so thanks for your great talk, Professor. So I have two questions. So the first one is you mentioned about this cosmic redshift. So I'm wondering how long is the distance required to make the photon appear the detectable expansion wavelength caused by this universe expansion? Is a few light year or 5,000 light year or maybe longer?
Sorry.
You're
asking what's the distance of what?
Required so that you can detect redshift.
Yeah.
Okay, this is a real expert question here, but I'll just expert here. Here's the problem: the expansion of the universe. The fact that the more distant an object is, the more the redshift is. Does that apply to things on Earth? Yeah, obviously not. Does that apply in this room? Of course not. The Earth. Does that apply in the solar system? Of course not. The space here is not expanding. The only reason maybe is because I was eating so much food there, but it's not the expansion of the universe. The galaxy is not expanding either, right? It's held together by gravity. So the statement that I said here, that you can use the redshift of distant galaxy light to tell how far away it is, very useful, only applies on fairly large scales, maybe hundreds of times bigger than the Milky Way galaxy. In other words, on the scales where you can approximate the universe as a uniform distribution of mass. If you look up closely, it's not very uniform at all. Right? And so Hubble expansion does not apply. But we're now talking about scales of millions of light years where it does apply. Okay. It applies very well.
Okay, yeah. The cosmic expansion does not exist between you and your girlfriend. far away.
Yeah. So my second question, I think you have partially answered, but I still want to ask: is there a limitation of the wavelength expansion, like from the red light expansion to the radio wave, or maybe longer? Is there any limitation?
That's a pretty fun question. There, it was discussed a little bit in some previous talks. You could have an enormous expansion from visible light. A very hot gas, for example, could be expanded so much by a factor of 1,100 times, so that today it was visible light, as bright as the sun. Today it is microwaves, and they're in this room. That is the most distant radiation that we've ever detected so far. It is the actual heat of the Big Bang itself, a few 100,000 years after the Big Bang, when the photons became free to travel, and they have traveled while the universe has expanded by more than 1,000 times. So that's the biggest we've got so far. It's going to be very difficult to go past that, although people are trying.
Yeah, 他就讲的说，他现在是说那个红位移啊，你现在看到是10跟11是最大的嘛，那能不能继续往下，你知道越来越早。但是呢，我们的视线就被 microwave background 微波那边 止住了。
We learned so much from that. The universe was completely different just a few 100,000 years after or during the Big Bang. It was amazingly uniform. No stars, no galaxies, almost no deviations from a uniform density, except a few very subtle, 1 part in 100,000 deviations. Those deviations, slight overdensity, eventually grew up to become our galaxy.
当我们回头看到微波背景辐射的变得很均匀，你完全看不到这些奇奇怪怪的东西，会有一点10万分之一的 fluctuation， 那就是我们后来星系的种子。但是那边就是我们视线停止的方向，在过去你是看不过去40万年，宇宙爆发之后的40万年。
So it's not possible like if the one object that is far enough and space is expanded enough, then for the Earth scale we can only saw this object as a long wavelength spectrum, but we
Right,
cannot...
you would need like a radio telescope.
Oh, okay.
JW, I guess, is limited to about maybe a redshift of 20. I mean, if we find that, that's a Guinness Book of World Record. I mean, that would be so incredible. Yeah. I don't think there weren't any galaxies before that.
Okay,
yeah,
thank you.
I just want to mention one thing, is when I worked with Matt at UCLA, we wrote proposals and write papers on high redshift quasars. And do you know how high that quasar is? Up at 2.5 to 3.5.
Right. For years when I was a student, 3.5 was the record.
Yeah.
And we just broke all those records in like a few weeks. They're just all
JWST in a few weeks.
Yeah.
但是 in 1990s, when we collaborated with mainland China, we used the Schmidt telescope to do BATC project. And I still remember, with all the Chinese astronomers and American, Bernstein, and Jeff Hester. And we poured those strong white liquor, 高粱酒. We hold strong liquors and toast each other and hope that and wish that we could find Z equals to 6 quasars.
Which at the time would have been spectacular.
Exactly. 就是那个时候希望找到红位移等于6的 quasar， 拿高粱酒一直在那边期待，结果现在很容易就到 Z 等于11了，完全想象不到的。因为 the reason I guess because JW is working on a pretty far out there in
as you saw, it goes to that's why it's so cold and why it has those infrared detectors. So it works out is 20 microns.
But it's
getting pretty difficult.
Technological possible to just go further down.
Yeah, I mean, I still believe it is technologically possible that JWST. I mean, I haven't really shown you the first galaxy yet, but I think JWST has a very good chance.
Yes, 他现在讲最重点是要找第一代星系，就是 first galaxies， 这是复数，所以就是第一代出现的星系。Well, Matt, I guess this is a subject versus the other one is first stars, right? First star, the first.
Well,
galaxies.
For me, the first galaxy means the first stars. Before that, it's almost impossible to tell there's just a blob of gas there.
Yeah.
It's thinking about making a star. So, yeah, that would. Yeah, I mean, here's the problem with astronomy. Isn't this a classic problem? If it doesn't produce light, we really don't know about it. Isn't that the problem of the dark matter? We don't know what most of the matter in the universe is. I'm an observer. I really need something to observe.
Yeah, dark matter, dark energy， 没有东西可以观测，所以它说需要光，但黑暗物质又不发光。好，还有没有任何问题 ？Okay, yeah, 赵伟 ，another person from UCLA, last one.
So thanks, Matt. I'm wearing the UCLA NASA T-shirt.
Awesome.
So
I'm trying the T-shirts UCLA 的话 ，OK.
So I have a question. So you mentioned, thank you for mentioning superstar clusters, which I'm working for my PhD as well. So you mentioned that a lot of discovery that is happening will happen. It will be some phenomena or some objects we never thought about.
Yeah.
And is that because we didn't understand the physics well, so we couldn't imagine this kind of objects that could be observed? And if so, then how do we study them? Since we are building the biggest telescope, space telescope right now, that JWST to discover them, and how do we study them in detail further? Thanks.
That's a tough one. In other words, could we open our minds more in advance to anticipate what the discovery is and go forward 10 years of scientific progress. If someone just had the idea, I think it does happen sometimes that a really smart person, sometimes even a rebel, maybe not a mainstream insider, comes up with a kind of a crazy idea. I listen to those crazy ideas once in a while. Usually they're garbage, but in a few cases, they might turn out to be true. The answer to your question is we should go back and make a list of the top 10 discoveries from Hubble and from Keck and see, why didn't those smart astronomers, including us, why didn't we predict that first? It's a number of reasons. Partly, yes, it's not knowing the basic physics. I mean, we have so little idea of the basic, you would admit this, it's your specialty, we don't know much about the basic physics of stars forming. We have a lot of empirical data, a huge amount of information, but a lot is missing, you would agree, right? And this is true for how galaxies form. It's true on many of these questions. So there are huge holes in the basic physics. In fact, the basic physics, I would argue, is often worked out after the observers show them our data. You notice how often that happened? But then there are other reasons too, that we knew a phenomenon, but we had no idea how important it was. We had no idea how big it was or how small it was. You know, we had the general idea, but we just couldn't imagine the specific case. That happened a lot with Hubble.
Yeah, and I once talked to another professor at UCLA, Ferdinand Coroniti. 他是个理论天文学家 at that time the chairperson of the institute. 那时候系主任。When I talked to him about observing proposal, first said, nowadays the referee of the proposal requires you to write down the introduction and your technique and your expected results. And you expect what you're looking for.
True.
If you already know what you're going to see, why should I give you observing time? But you cannot write a proposal saying, I don't know what I'm going to find out, please give me time, I don't know what I'm looking for.
Astronomers really have this problem. You want to do some astronomy that we have a high confidence it's going to work. Because it's an extension or a continuation of things we've been doing. We just do it more and do it better. But you want to have a little bit of room for really new ideas that will probably fail. I'm willing to, you know, I go to, what kind of, you have horse races here? Anyway, people gamble here. I'm willing to take a few gambles, even the odds are 10 to 1 against me, because I like the payoff. But we can't really base an entire observatory or an entire career on only long shot gambles. So we should play some of them, but we can't play too many of them.
Yeah, I guess astronomy is the first one that, well, the most important one that can show the essence of science, is that you're really looking into what you don't know. Okay, I guess we've run over the time, but I have to tell you that Matt has significantly simplified what he was going to tell us from his original PowerPoint. But
well, we can discuss it later, you know, for the rest of
the
week.
I believe they learn a lot because. Okay, great. Well, thanks, Matt, again.